What's up, guys? So we started today. Let me back up a slide here, where we kind of wrapped up today, actually, I should say, on this slide, where we talked about what we call the de Broglie hypothesis, de Broglie, um, and yeah, it's that and we actually ended up changing this up here. We said this is actually wave nature of particles. Right? So it's the opposite of what we've seen or talked about so far, where waves or light that typically or sometimes behaves like a wave can also display particle nature. Well, particles can also display wave nature. We drew these diagrams up here of the what we call the wave function that or the criteria that have to be met for allowable Bohr radii, right? So it has to sort of act like the electrons in these orbits have to behave like waves in where they're in that their wavelength, in this case we have to have one wavelength here and then two wavelengths here that are twice as long, and then there are three wavelengths here that are three times as long, and so on and so on. And I figured out that whole, the reason that we had that 27.2 instead of 13.6 for the energy. Ask me about that tomorrow, I'll let you know. So yeah, this is all about the fact that particles can behave like waves, right? And in that vein, right, we can say that particles, or we can actually characterize the wavelength of a particle in terms of its momentum. All right, so this is a big equation, a big relationship you'll have to use. All right, this also allows us, we can write this in a couple of other ways. First, we could say that lambda is equal to h over mv. All right, um, for a particle, we can figure out based on the particle's wavelength what its speed must be, if we know its mass, of course. And then we could also say this: we know that lambda is, let's see. Well, I'm going from this. E is hc over lambda. Okay, so therefore lambda is hc over energy. Now this is of a photon, right? We can say this for a photon. Now, photons don't have mass, hence I'm erasing that one. But we can say that for a photon, we can talk about it, even though a photon is a massless, what do we call it, a massless particle, we can still express a photon's momentum. Because now we can say that hc over E of a photon is equal to h over momentum, right? So we just took this and combined those two expressions. And then we can get rid of these, get rid of those h's, and we can say that energy of a photon is equal to momentum times c. All right, so there's another equation that we'll end up using once in a while. Okay, now the thing over here, what this means for the Bohr model, well, that's the whole thing we got to, where the radius of any energy level is the Bohr radius times n squared, right? And here's what we call the Bohr radius. Okay, my color scheme is changing. Okay, so that's that's stuff we saw this morning. Okay, but the important stuff really going forward, I guess, is that. Okay, next page. So we take that idea that photons can have momentum. All right, um, based on their wavelength. Right, the bigger the wavelength is, the smaller the momentum is, and vice versa. All right, so what we're able to do here, or get into, is the idea that we can actually fire photons at electrons. All right, so a photon's like a particle of energy, an electron's definitely a particle. And these collisions, and this experiment demonstrates what we call Compton scattering. All right, so you fire this photon at an electron, and the two things, well, the interaction acts just like an elastic collision, an elastic collision, not an inelastic, an elastic collision. And here's what we can see, right? From our diagram, we have our incident photon here with a certain short wavelength, right? Which means, well, short wavelength means high energy, also means high momentum, right? Based on this. And in the end, so a scattered photon has, well, here's what we call our scattered photon. Well, its wavelength has gone has gone up, right? We can tell its wavelength has gone up. Therefore, its energy and momentum have gone down. It's lost energy and lost momentum. Well, that makes sense because there's been some collision that's happened here. All right. Now, because this, remember, this is elastic. There's the bell for the end of the, excuse me. Because this is an elastic collision, energy, well, kinetic energy is conserved. All right. I mean, total energy is always conserved, but in this case, kinetic energy also. But you know, some, I'll say, energy and some momentum are given to the electron. All right, so if we actually know how much energy, you know, if we were to say figure out what speed this had, all right, we could figure out how much kinetic energy it had, and therefore we could figure out, based on the energy this one had, well, how much energy must this be left with, and then we could figure out, well, based on its energy, you know, we could say, oh, okay, now I know what its new wavelength is, and now I know what its new momentum is, so we can go through all these sort of steps, you know, using conservation of energy and or conservation of momentum. All right, so that's called Compton scattering. Next, really, really neat experiment called the Davison-Germer experiment. Don't know how well you can see this in your notes, but what these dudes did, it says here, hot filament to release electrons. A couple ways to get electrons off of metals. One way is literally to heat up the metal, all right, and that will, for reasons that, you know, I honestly can't explain too well, heating up that metal will eject electrons. I think it's just, you know, pure vibration of the particles, you know, allows them to escape, allows the electrons to escape the atoms. So we get those electrons to escape their atoms, and then we accelerate them through a potential difference. We've seen that question before, where we have, say, like, you know, this, and there's electrons here, and here's a potential difference, delta V through there, and we said, okay, by the time this thing gets here, we'll have accelerated through that potential difference. Some work will have been done on it as it accelerates, and we could actually find its speed here, all right? So anyway, these guys shot electrons at nickel crystal, right? Over here is a representation of the atoms in a nickel crystal, very nicely organized, equally spaced in that crystal lattice structure, right? And, you know, if we go back a couple days to talking about double slit, you know, we shine light at double slits, and it acts like two sources, right? And then we get out here, we get, you know, bright spot, dark spot, bright spot, dark spot, and so on, right? Well, this works even better if instead of a couple of slits, you use lots and lots of slits. For that, we said, like, the more slits we use, the sharper these maxima get. So we might get, like, real fine dots like that. It's called a diffraction grating. This thing's called a diffraction grating, those lots of little slits. Well, you know, based on this wavelength, right, we can predict, well, really, what this angle should be. This is, you know, really our two-source interference stuff, right? No-brainer. Now, what Davison and Germer did was they took these electrons and they fired them at this crystal lattice that had very ordered spacing of, well, atoms, right? And what happened was, these are electrons that they're firing in here, but saying that, okay, they're electrons, and with this new idea, we can say that they're particles that actually have a wavelength, right? They have wave nature, even though they're particles. Well, based on the same exact theory we use to do this stuff, they said, where should these things, well, not pass through and go out like this, but bounce backwards, for the same reasons, though, right? Treating them just like a diffraction grating. What angle should they bounce back at based on, you know, again, the same exact idea as that? Well, based on wave theory, they said, well, they ought to come out at a, well, an angle like this, right? And what happened was, where's the actual answer? Oh yeah, so we got, you know, they got these things to scatter out to angles, right, that were almost exactly what wave theory predicted. Okay, so pretty awesome stuff. That, I mean, real experimental proof that exactly that particles can act just like waves. All right, so I think there's no questions really to ask about Davis and Germer other than, you ought to know what they did, all right, that they shot electrons at nickel crystal, and, the results of it showed that particles behave just like waves. Okay, I'm going to go back a slide, or maybe two slides. Yeah, and there's a great question in the book. It says, well, geez, if particles are waves, I have momentum personally, right? I have mass. I can move at certain speeds. Should I be concerned about, walking through a door and behaving like a wave, and then, I'll end up getting diffracted and, end up with maximums of me here and there? Is that something I should worry about? Well, it isn't, because at the end of the day, my momentum is pretty darn big, right? H is really small, which means my wavelength is like really, really, really small, right? If I'm a particle, my mass moving at typical speeds I move at, we would say that my wavelength, my de Broglie wavelength, is very, very small. And then what we're saying is, well, if we have like a huge, here's a door, a meter across, right? If we have, little tiny wavelengths like this, there's really no, even if they're, really tiny wavelengths, right? If this dimension here, what we call D, is really big compared to the wavelength, not much happens, all right? Really, really nothing happens. It's only when D is on the order of the wavelength that some actual bending of the waves happens. Right? So we don't have to worry at all about being diffracted as big, huge particles. It only happens for little tiny things, right, with little tiny momenta, right, especially as compared to H. Okay? So never fear, you can walk right through the door. That's all, folks. I am emailing you also a homework assignment. Okay? Should be pretty straightforward, I think, and I'll see you tomorrow morning. Thanks.